So if we manage to finish this one, we'll be left with 2, isn't it? 4 and 5. We'll be left with 4 and 5. Did we do 4 and 5? No.
No, we didn't.
We only did 1 and 2, isn't it? Okay. So this was the question of calculating the principal moments of inertia of a uniform solid cone. And you were given the vertical height h and the base radius a about its vertex for a value of ratio h over a is every axis through the vertex principal, the principal vertex, a principal axis. Okay, for this case, find the position of the center of mass, the position of the center of mass, the principal moments of inertia about this center of mass. So in other words, we just want to find the principal moments of inertia about this center of mass. So remember, a center of mass, if our object is in 3 dimensions, like I indicated the other day, that we are dealing with an object in 3D. This is a cone in 3D when I drew it like this the other day, to indicate that this is the z-axis, and then this is the y what? The x-axis. This is the y-axis from your calculus. So if you are to draw a cone along this axis, so which means you are going to draw a cone. All right. So the one which they are referring to as the base radius, it's there at the vertex here. The base radius is there at the vertex. It means it will be a cone here at the vertex, which something look like this. So the base is there at the vertex of the cone. So which means the x-axis, and then we know the radius at the base, this radius, that is what we are referring to as A, the base radius A, this one, the base radius A. And then we are obviously having the z-axis, which is going upwards. So that is how our diagram is looking like. The base radius, which is going upwards. All right. And then R, which is the radius. So let's analyze the question here. We are saying let the cone's symmetry axis, which means the position, the symmetry axis, the position which we are going to divide the cone into half. So this is the axis of symmetry, which is the z. If you are to cut this cone into half, which means you are going to divide it through the z-axis going downwards, then that's how you are going to divide that cone into half. So let the cone symmetry axis be the z-axis. So that's why the cone is facing upwards. All right, which implies that vertex at origin, I have put the vertex at origin there, which means the base of the cone, such that the base z which means that is our base z. Here, this is the base z, the base of z here. That's where our base z is, which means is the initial height h. So that base at z, the height of h is the same as the height of h, which means h is increasing with time. How big the cone is, so h is also increasing here. As the cone becomes bigger, h is also increasing, which means h is starting from the initial vertex point, going upwards. That is h. H will be increasing at any point given time. there will be an H. So H is changing with time. There will be an H, which can be here. This is H. So H is changing with time. So initially, when the cone is at origin base Z, Z is equals to H. That is what we are having here. So which means at height Z, the cone's radius, which means the radius at height Z, the cone's radius is given by what? The function R of Z is equals to A over H Z. So at any given point in time, if I want the radius from here to there, at any given point in time, the radius from the center to the cone at any given point in time, which means that radius is given as a function of A over H multiplied by Z as a function of Z. So at any given point in time, the radius at any given point in time is the radius R is A over H multiplied by Z. Any question there up to here where you'd want to ask before we go any further? The radius in terms of Z. So which means R as a function of Z is just A over H multiplied by Z. Hello, we are quiet, pair. Guys. Hello.
No, we don't have a question, sir.
Right. So let's move on, say. If you are quiet, maybe I think you are still processing. So in other words, in short, you are just saying R of Z as a function of Z. R is a function of Z, which means the radius at any given point in time. The radius at the base, the radius at any point, as Z is increasing, the volume of the cone is also increasing. Remember, we are not given a height as a constant. Height H can be any H is increasing with time. So which means it will be A over the height multiplied by Z, which means Z is the function of R. That is the relationship of R with Z. It's A over Z multiplied by Z, A over H multiplied by Z. Then we just bring the dimensions of mass in terms of volume and density. That symbol rho, which looks like a P, which was bent, like which I told you, rho, it's just the density. Density we know is just mass over volume. All right. What is the volume of a cone? Volume of a cone. This is the volume of a cone. It's 1/3 pi r squared multiplied by the height. It's 1/3 pi r squared multiplied by the what? By the height. So in place of r, in place of the r, we put the what? In place of the r, what did we put? Instead of r squared, what was replaced there? Hello? Instead of r squared, what did we put?
Pi a squared h.
Yes, that's what I want you to see. Because volume in standard, anywhere you ask, even if it's maths or whatever, if I ask you what is the volume of a cone? Volume of a cone is just pi r squared multiplied by the height. So if I know the radius and I know the height of the cone, I can be in a position to calculate the what? The volume of the cone. Is that clear, class? Yes. So here, since at the base here, why did we replace with the A? At the base of the cone, assuming the cone has not moved any radius, any height above, the radius, that R is the same as also this initial base area, base radius, when the cone is at the vertex. So R, this is the base. It's not upwards, it's still on 2D plane, which means this plane is at the surface. It's 2 dimension at the bottom. Okay, so the radius, which means the distance from the center to the point there on the circumference, that's the radius. The distance from the center to the point here on the circumference is the radius. To the circumference, the radius. That is A. To the circumference there is the radius. So that is our A, which we are referring to there. So you can replace where there is R, you replace with the A. That's how R vanished here from this substitution. You will notice that we are no longer going to deal with the R anymore. R disappeared here when we replaced with the A. R has already disappeared. Then we come now, we want to calculate density using this volume which you are having. So where we know that what is the density is mass over volume. So I know my mass is let me show you how that formula was derived so that you don't memorize these things. Density, so this one you must know it by head, volume. Then when you are from there, now you say your mass. Your mass, you write your mass, which is M over volume. What is volume? It's 1/3. You write your 1/3 pi, you write your pi, and then you write your A squared multiplied by what? By H. So if you divide by 1/3, it's the same as multiplying by what? By 3. Here you are dividing by 1/3. Remember, we are saying the volume of a cone, this V, which is at the denominator, it's 1/3 pi R squared, which is 1/3 pi A squared, H. So 1/3, which you are dividing by 1/3, is the same as multiplying by what? 3 over 1. That's why this 3 is now on the what? On the numerator. I removed it from the denominator only. Is it clear? I removed the third on the denominator. It becomes a 3 on the numerator. It's just like saying, what is 4 divided by half, class? What is 4 divided by half? If I say what is 4 divided by half, then it's 4 times 2. You use the inverse operation here, which means it's 4. Instead of using division, the inverse of division is times. Then the inverse of 1 over 2 is 2 over what? Over 1. So this is the same as removing 4 over 2 divided by 2 can be written like this. 4 divided by what? By half. Can you see? Can be written as 4 divided by what? By half. So what I'm trying to show you is that 4 divided by half can also be written as 2. This half you can put on the denominator, which is 2 times what?
4.
Times 4, which is what they used here. Instead of dividing by 1/3, you can also say it's times 3. That is how we came with this formula for density in terms of A. We are just running away from R. So we replaced R with A. So that is the first part, which you must know. Now we are calculating the moment of inertia in the Z. The moment of inertia along the Z axis. So this is what we are going to calculate, the moment of inertia along the Z. So this I is representing the moment of inertia along the Z axis, the moment of inertia along the Z axis, which is, what is it given by? Is given by the integral of R squared dm. Dm is the mass, m, which is representing mass. So R, and then the integral of R squared dm, which means these formulas you might be given in an exam. I will check where there is a formula, where there is a question in classical mechanics which dealing with moment of inertia. Then we check the formulas that you'll be given. But normally you'll be given the formula for the moment of inertia along the Z. What they would want to know, how we are going to substitute that formula. All right. So let's start now. We know that the moment of inertia, what is mass in terms of, if you are to replace this formula, you want to calculate mass. Mass is given by what? If I'm to ask you, in terms of density and volume, how do you write mass in terms of density and volume? If you are to make
It's
M,
density multiplied by volume.
yes, it's density multiplied by volume. So M is equals to density, which is rho, multiplied by what? The volume. That is correct. So, all right. So, which means since I want the moment of inertia, I'm differentiating that mass, dm. So, which means I'm going to the r squared. Remember, the r squared is coming from the formula itself of the integral of calculating the moment of inertia along the z. So, the r squared is remaining as it is, this r squared. It's staying as it is, which is here. We did not manipulate the r squared. It's remaining as it is. That is the r squared. It's remaining where it is. We never did anything to the r squared. But we played with the mass. Instead of using dm, can you see the dm? You are not seeing the dm, this one? Yes, change in mass. That is the one which we said volume, density times what?
Times volume.
Volume, yes. So the density is this rho, which is outside the integral. The density, which is this rho, which is outside the what? The integral. Is that clear? Now, we are going to the volume element. The volume element. The volume element, it will be r, dr, d theta, dz. That is the volume element. So r, which means if it's a cone, it's of radius r, like this. So your theta, the theta, remember this is the theta which you are referring to, theta. So theta is ranging from what to what? If you are going to talk of that theta, which you are referring to, it's ranging from what to what? The angle theta of the radius. It's ranging from what to what? The theta of the volume of the cone. Remember, when you circle the cone around, how many degrees is a cone, is a circle? If you are to move around the circle, you are starting from 0 and you move around the circle, how many degrees are you going to rotate?
360.
360 degrees. That's when you're going to form a circle, 360 degrees. So the r which you are referring to, it's the volume. Volume is integral. We are talking of the area which is covered by that radius r. Then now we are differentiating it. We are taking the integral, which means the theta is running from 0 to 360 degrees. That's why here it's written from 0 in terms of theta. This is theta. It's corresponding to the second integral. This is theta. It's corresponding to this second integral, which means the dimensions for theta are starting from 0 to 2 pi, which means it's rotating 360 degrees, starting from 0. Then, when we are looking for the volume of this cone. When we are rotating this cone in the direction of what is it? R. In the direction R, it's from 0 to H. In terms of dr, it's from 0, this one which we drew here, our r. Remember we said r is a relationship of a over h. It's multiplied, r is equal to a over h multiplied by z. So the radius, where is it starting from and where is the radius? going to end. That is what we are going to be using now. So the radius is going to start from 0, ending at A over H multiplied by Z. So that is the domain of theta, is starting from, theta is an element. If it's maths, it will be saying your theta is ranging from, your theta is ranging from 0 to 2 pi. When you are looking for this region, you are given that. And also your R is ranging from, starting from 0 up to A over H multiplied by Z. That is the range. Not the range, but the domain of R. Then when you go to the domain of Z, Z is starting from, remember we said our H is this one. This is the H, which is going along with the Z, any point in time, but starting here at 0. That is the, let me use a different color, maybe orange. Yes. That is our H. H is moving at any given point in time. This is along H. So it's going to start where H is 0 there. At any height, that height, we don't know it. That's why we are calling it H. So which means our Z, this Z, which we are having here, the outside, and this also is the outside, which is corresponding to Z. So Z is also greater or equals to 0, but Z is less or equal to H at any given point in time. So these are your limits when you are integrating. You are integrating with respect to, whenever you want to replace volume, that's how you replace the volume. The V, remember we said density, we said mass, that dm, we replace the mass, dm, by using density, which is rho, multiplied by the volume element. So r d theta is replacing the volume element. Whenever you replace d, v, you are replacing with r d theta dz. Then we integrate. Why is there r squared? I told you that r squared we did not change it, because that is the formula of moment of inertia along the z, not of any shape, but of a cone. So you'll be given that the moment of inertia along the z-axis of a cone is given by the integral of r squared, which is the radius dm, which means you are integrating with respect of the mass, if you know the mass of the cone. So now we put it in 3 dimensions, rho, then it's the constant, which is multiplying everything which is in the integral. We skipped a lot of steps of integrating, which are supposed to be there. So the calculus itself, when you integrate correctly here, which means everything, it will take you to pi multiplied by rho over 10 a squared a to the power 4 times h. If you integrate this correct, which means you are going to integrate the first one with respect to r, and already there's an r dr there. Then you substitute the limits, you integrate again the second one with respect to theta, you substitute the limits, then the last one you integrate with respect to what? To z. Then you substitute the limits, which is 0 and h. If you do it correctly, we skipped these steps for mathematical part. So if you integrate it correctly, you are supposed to come to here, which is pi multiplied by rho over 10 a to the power 4 times h. So here we skipped the mathematical part of integrating. We assume that you know how to integrate, because the physics part, it will be done. What will be left part is just the mathematics of the integrating part. So if you are correct in your integration, you must be knowing that I must arrive at this point. So now, once you arrive at that point, It's just a matter of now manipulating so that we bring in back the mass. We must bring in back the mass. And also the H, it must also disappear. How is it going to disappear? Let's go to rho. On our formula, where we used rho. Rho, we indicated it. How did this disappear? We said our rho is equals to 3m on the numerator divided by pi a squared multiplied by h. So which means if I get this answer, which I'm having there, you manipulate it like this, which is you are given pi. When you integrate correctly, pi p, which is your rho, divided by 10 on the denominator. And then on the numerator, you are multiplying it by a to the power 4. And there is an h there, which you are having there. Right. But what do we know about rho? That rho p. What do we know about rho p? So we know the rho p, which we are having there, it's m. That rho p, this one. We know it's 3m over pi a squared over h. So that is the one that you are replacing there, the rho p. So that you see what you are going to be left with, because this is what you are having already. So you replace this p. Instead of writing that p, we are replacing with what we already have for rho, which is 3m. So which means here, I'm no longer going to write rho. I replace that rho with 3m. So I will cancel this rho. Then I write myself 3m. So when I put 3m divided by pi, this is the pi, which is the a squared multiplied by h. Then you indicate it. It's pi a squared multiplied by h. So I have cancelled the rho. Then I replaced with the ones in blue, so that the h and the h cancels out. Then a squared at the denominator cancels with the a squared, a4 on the numerator, but there will be a squared. Now there's no a on the denominator. Then pi cancels with pi. Then you are left with 10 on the denominator. So in other words, your answer is just 3m a squared multiplied by h over 10, which is this answer which they are having here. That's how they got it. The h, remember, we cancelled it out, so it's not there. The h on the top and the h on the numerator is out. So it takes you back to this answer. Any question there about the moment of inertia along the z?
Yeah, I have a question.
Ask it.
I didn't get the part where you were saying, you said the derivation of r with respect to m, dm. Okay, the first part, we found the density, the first part there. You see the after the equal sign you wrote density and then 0 to the power 0 and h. So I didn't quite get that part on how you found those values there.
Which ones?
Where you are deriving, yes. The where you wrote with a green marker. You see the r squared dm, and then you said is the moment of inertia with respect to z, right?
No, not with respect to z.
Mm.
It's the moment of inertia along the z-axis.
Z-axis.
Along the z-axis, yes, not with respect to that. Along. It's a moment of inertia when it's turning along the z-axis. Yes.
Okay. Can you please explain this part for me? The where we have the density and the derivation, and then a0 and h.
I replaced dm with v. dm with v. We told you the volume element here. Mass is equals to what? Density times?
Density multiplied by volume, yes.
Yes. So if I want the dV, which means dm, here I also have what? d rho dV. So the dV is in polar coordinates r, theta, and z. In polar coordinates r, theta, and z. This dV, you can also write, remember we said mass is density times what? Volume, isn't it?
Yes.
So if I want dV, that's what I'm saying. If I want dm, to replace dm, which means I must be having rho d what? dV. Do you see? Is it clear now?
Yes, it is.
It is clear.
Yeah.
So, so that dV is given by r, dr, d theta, dz. dV is the same as r given by the dimensions which are here, which is r, d, dr, d theta, dz. And then the limits that you are going to integrate, r you'll be integrating from 0 up to a over h multiplied by z. Theta you'll be integrating from 0 up to 2 pi. And z you'll be integrating from 0 up to h.
I want to
Then,
understand. Sorry, I want to understand how you got the limits.
but the limits I was explaining, if you tell me you're not listening.
I was, but I was trying to understand. I didn't understand them.
Then you won't finish the question if you are behaving like this. You will never finish this question. I'm saying z is ranging from 0. This is the 0 which I said. This is the z-axis, the one which I was talking about. This is the z-axis which I label. It's ranging from 0. You can't say from 0 to h, from 0 to z. No, z is ranging from 0 to any height h, which I labeled in orange that time. I put it in orange to say z is starting from any height at the base or at the vertex, from any point at the vertex there, from 0 up to any height which is represented by h. We don't know where this cone is going to end, but we know that height where it's going to end, it's h. So which means the limits of z, they are starting from 0, which is the vertex, the origin, ending where? At any height, which is what? H. That is the volume, that is the height of the cone. I don't know if you are answered.
Yeah, I am.
And then theta, I told you, the circular, starting from theta 0 up to 360 degrees, because it's turning, it's the whole side, it's turning the whole angle. Where is the theta coming from? Theta from 0 to, remember when you are calculating the volume of the whole cone, going upwards, our dimensions are like this. Our dimensions are like this on the, at the base of the cone, the theta which you are referring to. For example, like this, the base of the cone, in terms of x and y. This is the base. So our theta, we are saying it's rotating from here, the cone, 360 degrees, the base of the cone. Now the cone is moving upwards, starting, so which means the base which we are taking, theta, is starting from 0, rotating the whole of it, 360 Degrees.
Degrees.
Yes. So that's why degrees in radians is what? 2 pi. 2 pi radians. Is that clear? That's the limits for theta, which is the angle. Yes. The reason why we are changing these limits, we want to put them in what? In cylindrical coordinates, which is r theta and what? And z. So I must have a limit of theta. I must have a limit with respect to r. I must have a limit with respect to what? To z. So once I have those limits, I'll be able to integrate and find the volume element. That's why we're doing it like that. So theta is ranging from 0 to 2 pi because it's a circle. Then the last limit is this one for r. We told you at the base, r is the same as a over h multiplied by z when we're starting here. This problem is. So which means starting the radius is always starting from 0 at this point. So I'm starting my radius, it's always here, 0, until I move a certain distance. This distance which I'm going to move, this is what I told you at the base. At that distance, it's a radius. So this distance which I'm moving at any given point, that radius, you are given it as a over h multiplied by z. That is the one which I told you from the beginning. To say this r, if I want to replace with r, I don't want to use r, I'm going to use a over h. Then I will multiply that a over h multiplied by what? By z. So where am I starting from? From the origin. At origin, the radius is 0. I have not moved anything. The moment I started to move, the radius was not given as a constant, as a number. It was given as a relationship between h and z. So which means that a over h multiplied by z. That is the relationship which I'm having as my radius at any given point in time. Whether I'm moving this side is still a over h multiplied. Whether I move this side, then this is the base of the cone. Then I go upwards. I'll be moving upwards. Now the z, the h is also increasing. I'm forming a cone, etc. So those are the limits. So I have shown you how we derived that the moment of inertia in the z is 3 over 10 multiplied by m a squared, where we replaced the rho. We just replaced the rho by just replacing rho with 3m over pi a squared h, and then some units cancelled, like h and h, like pi and pi, they cancelled out, and then the a squared cancelled with the a to the power 4, then the a to the power 4 was converted to a squared. So we are done with that one for the moment of inertia in the z. Even in an exam, you must be able to set up this. It won't give you a problem, this one. There is nothing that is difficult for you to remember there. Just you are given the moment of inertia is just the integral of r squared dm. dm is, you are differentiating the mass, m for the mass. Iz, its moment of inertia along the z. Integral of r squared dm is the formula. You are replacing. You know that mass is density times volume. So if I add dm, it's going to give me d rho p. But p, density, is a constant. You can take it out of the dm, dv, then you put it outside the dv, which means dm is the same as rho dv. What is dv? It's r dr dt. That is dv. So that is the volume element. When I am to replace with dv, r dr d theta dz, then you are done at this point. That's how you replace the volume element d, dv. So whenever you are having dv, you always replace with r, dr, d theta, dz. Even when you are putting your integral, you make sure from calculus, the inner integral is the one having the limits of r. That's why here, our inner integral is having the limits of r from 0 to a over h because of the dr here. The second limit is going to be with respect to theta because it's from 0 to 2 pi and you put d theta. The outside limit dz, it corresponds with also the limits 0 to what? To h. Any question? Remember, it's 33 marks. 33 marks. So now we are here, this second part. The moment of inertia about the axis through the vertex. So at first we were talking of the moment of inertia along the symmetry, the cone symmetry axis, which is the z-axis. So now we are talking of the moment of inertia through the vertex, which means it's not through the axis, the vertex at the base. It will be the same with the one moment of inertia in the x, it will be the same as the moment of inertia in the y. Why is it like that? Because at the base, it's like this. At the base, it's just like this. So this is the vertex which they are talking about. Y is coming through there, and then x is going through there. The effects of these x's along the vertex, they are all the same. It's just passing through the center. And also that one is passing through. So this is the moment of inertia along the ix. This one will be the moment of inertia along the iy. So this effect of these two passing through the vertex is just the same. However, they are different with the moment of inertia along the symmetry line, which is iz, along this axis, which is iz. So that is the first statement that you must indicate, that ix is the same as iy. Using cylindrical coordinates r, theta, and z, what do you know about x? X is r cos theta. X is r cos theta. Your z is here, like that. And then this is your diagram. Z is like that, so that you know where it's coming from. This is the x. This is the y. And then the radius is anywhere along the end. This is the component. So this is the component of the radius. So that radius, it has moved a certain distance in the x, and it has moved a certain distance in the y. So I want you to see where the theta is coming from. So this is our radius, which is, it has moved some certain distance in the x, it has moved some certain distance in the y, like that. So if I want that r in terms of theta, this r, this is the one which we are saying theta, r is the same as x. This is our x, this x. And then this is our y, which we are referring to as y. And this is obviously to be 90 degrees because this is the height, which is the z. So here there's 90 degrees. So if I want x as a relationship of r and the cos, so we are saying the side that is opposite the angle theta, the radius, remember we even mentioned here that this is our r, the base, at the base of the cone, we indicated it as r. Sorry, we indicated it as r. So if I want this x, which I'm having here, and if this is my theta, the angle which I'm moving, so if you indicate it as theta, you are moving. Remember we said you are rotating the whole angle. That's why our theta was starting from 0 to 360. So if I'm having r, what is the relationship between x and r? And the r is the hypotenuse. And where those two meet, remember here we are having a 90 degrees. There's a 90-degree angle here as well. So what is the relationship between r and y? And what is the relationship between r and x in terms of theta? You can see it from that y is parallel. This is y-axis. This is x-axis. The top one is the z-axis. This is the z-axis. So you must be in a position to draw these diagrams in 3D so that you can see them proper. So if you are to continue with the cone is going to go up, draw that cone like that. Then the cone is out. So this is the base that we are referring to say that r at the base. What is the relationship in terms of x and y? So y is always r sine theta. Why are we saying r sine theta? Because we say sine theta is equals to opposite angle to theta, opposite side over the hypotenuse. So if I want y will be r sine theta. That's where it's coming from. If I want x will be r cos theta. These are trigonometric ratios for grade 10. Any question there? How they obtained x is r sine theta and y is x is r cos theta and y is r sine theta in relationship to the diagram. Any question?
Yeah, I think it's making sense.
It's making sense. You are referring to the base of the cone. Remember that one was our r before we converted it to a. That was the original radius before we converted it to a. So we are saying that radius there, r, can also be given as x in terms of r, y in terms of r. So using the cylindrical coordinates, r, theta, and z, now we want to integrate now. So which means we are here. Now we want to integrate. So what does it say? If you want the moment of inertia along the what? If you want the moment of inertia along the what?
The x-axis.
The x-axis. You say the integral of y squared plus z squared d what?
dm.
Dm. That is the formula which you must memorize. And if you want the moment of inertia, also it will be the same because the moment of inertia along the x is the same as the moment of inertia along the z. Remember we mentioned it here, that the moment of inertia, if I know the moment of inertia in the x, that moment of inertia in the x is the same as the moment of inertia in the what? In the y.
In the
Yes, so there's no need for you to be calculating the moment of inertia in the y because you already mentioned that the one in the x is the same with the one in the y because they are all passing through a what? A vertex. Is that clear?
Will I be wrong if I write the limit of derivation with respect to z, the a over h times z? If I write r, is it wrong?
If you write,
I replace the a over h times z and I just write the r.
the question, it won't work because at the end of the day, we have been given a ratio which was given a over h. You remember on our question? It's not going to help you to find because you were given that the ratio a over what? H over a. Yes, so you need to use it. So how are you going to use it yet you have already eliminated that h over a? So for what value of the ratio h over a is every axis the vertex. Is every axis through the vertex a principal axis? So we are looking for this value of h over a. So for what value of the ratio h over a is every axis through the vertex a principal what? Axis. So every axis through the vertex is a principal axis. So you need that value of h over a. So if you're not having h over a in your equations, or anything that is relationship related to a and h, and you replace it with r, then how are you going to get the answer of that ratio?
Mm.
However, the question will be answered to say, if I have r, will it assist to, yes, you can integrate, but in this problem, it won't help you if you put the limits in terms of r. They won't assist to solve. So we do the same like what we did. The moment of inertia in the x is given by y squared plus z squared dm. Can you see dm?
Mm.
Yes. The previous one, moment of inertia in the z. So you write your moment of inertia, I, in the z, was given by the integral of r what? R
Squared.
squared d what? dm. M, which is referring to the mass. Now, the moment of inertia in the x is the integral of y squared plus z squared dm. So where there is y, you replace by r sine what? Where there is y, you replace by r sine theta. Remember, we said r sine theta is y. So r
Mm.
squared sine theta, it will be y squared. You replace your dimensions. You bring in the r. All right. Then the z, because why are you replacing your dimensions? You say they must be in the form of dr, which means if I have a function in terms of r, it's fine. If I have a function in terms of theta, I'm also fine. If I have a function in terms of z, I'm also what? Fine. These are the dimensions. And what is this volume element? This is what we are referring to as dm. dv. This is d what? dv. That's our dv. And this middle term is what we are referring as y squared plus z squared, this middle term. So dm has been replaced by that rho. If I add it here, it will be rho dv is equals to dm. So we have replaced that. Everything stays the same. So that rho is this rho. dm is equals to on the left. Everything is clear. So if you know how to set up your integrals, we are fine. The limits have not changed. Everything is from 0 to h in terms of z. Everything is from 0 to 2 pi in terms of theta. Everything is from 0 to a over h multiplied by what? By z in terms of r, the radius. So the only trick, it will be just to integrate, because maybe you wouldn't want to memorize this. So you must be in a position to integrate proper, which means once you integrate properly, before we remove the a and the h. Remember, we said the answer here was in terms of rho. The first one that we got. We are having a rho here. Can you see that rho which we're having here at first? Or z, when we're dealing with z. Can you see the rho here? This one.
Mm.
Yes. When you multiply by rho p. So even with this one, the p you have multiplied by rho p there, and then you simplify it. Like what we did here when we're dividing to say rho is 3m over a squared multiplied by over pi a squared h. 3m over pi a squared h. So it's same thing. There's a step that has been skipped because our answer, can you see this answer does not have rho? Are you seeing this answer does not have rho? Hello?
Hello.
Are you seeing that this answer here does not have this P, which we are multiplying by? After you are done integrating everything, what are you supposed to do? You multiply everything by what?
By P.
By P, which is that row. And then after you're done multiplying everything by P, you divide. You are going to divide by this 3m, where there's that P. Now you replace P with 3m over pi multiplied by a squared multiplied by h. Then when you are done, that's when this final step came out, this one. So this statement just came for the effect of that saying, since we already concluded that a moment of inertia in the x is the same as moment of inertia in the y. However, there is a step that has been skipped, how you canceled the row here. So you must also practice how to integrate this on your own when you have time. The first one and the second one, so that you can also see how the row disappeared. Then you see, are you really coming back to this answer on your own? So you'll be practicing. Of course, when you're writing the assignment, you may skip the step. However, it will add more marks if you include the steps how you were getting rid of the row as well. All right, so these x's are the principal by symmetry, which means Ix, axial symmetry, Ix is equals to Iy. Off diagonal terms, they vanish. So when is every axis through the vertex a principal axis? So every vertex is going to be a principal axis under this condition. That this happens if the inertia of the ellipsoid at the vertex is spherical. In other words, the moment of inertia or in the Ix is equals to the moment of inertia in the y is equals to the moment of inertia in the z. So in other words, you are now making an equation, which means at first you found your moment of inertia in the what? This was the moment of inertia in the what? Which we calculated first in the z. It was I in the z. So it's an equation. I in the z is now equals to I in the x, which is also equals to I in the what? In the y. Because these two, we said they are the same. So we formed an equation. Then we brought this moment of inertia that we calculated here, so that we can be in a position to calculate the principal axis. The principal axis only occurs when the axis in the x and the moment of inertia in the x is the same as the moment of inertia in the y is the same as the moment of inertia in the x. So now I'm solving now. What is that value of A that is going to satisfy that condition? So it's a matter of solving for A. So let's do it. In other words, we find what is the value of A squared. So it's just a matter of mathematics there. So we are having 3m. Okay. Let's solve the right-hand side so that we can be a bit faster, which implies that 2h squared. Where is the 2 coming from? What did you multiply both sides by? Can you see there's a denominator here, which is 5? Are you seeing the 5? Hello?
Yes.
Are you talking about the one that you obtained when you were doing moment of inertia with respect to the
Yes.
x-axis?
Yes, to the x-axis is the one on the left, this one. This is the moment of inertia of the x and the y. Then you
And the
equate
y.
it to the moment of inertia in the z, the one that we got in the z, which is 3m over 10. Yes. So now you want to find a relationship. We are getting rid of the common factors, our m, and then since our idea, we were interested with the ratio. What value of that ratio, A over H? It is, isn't it? Remember, our question is asking us, what is the value of that A over H when it is a principal axis? what value or what ratio A over H is every axis through the vertex a principal one axis. So we are no longer interested with the M. We are only interested with H over A. What is H over A? So let's get rid of other values which we are not interested with. Once you reach here, once you have equated the moment of inertia in the Y and the moment of inertia in the X in the is equals to moment of inertia in the Z, we are just equating those two equations. Once we equate these two equations, it means that, which the implication sign, you have multiplied both sides by what? Let's divide. When you divide both sides by 3m, what do you get? You are dividing each side by 3m. Can you see 3m? Here, I divide by 3m. What I do on the left, I do on the what? On the right. Then here, I also divide by what?
3M.
By 3m. So which means the 3m is going to disappear, isn't it? So which means it's assisting me to get to my conclusion of what is the relationship between only A and H. So which means this goes, it's done. But I'm left with that 10. I have a 10 there, and then I have a 5 that side. What can I do there? If I multiply both sides by 10, what am I going to get? Here I multiply by 10, I get A squared. This side I multiply by 10, I get a 2 as a numerator. Is it clear? So 2 times H, I'm getting 2 what?
2H squared plus.
Yes. Then this
Plus.
2 multiplies this figure, but the 2 multiplies the denominator there. So 2 into 2, 2 into 4 goes how many times? 2 times.
2.
So that's where this A squared over 2 is coming from. Are you clear there? Are you seeing it? Then on the right hand side, what are you having? A squared, which is this one, A squared. Can you see? Yes. So now, once I have the A squared, what is left now is for me to find the relationship between H and A. So which means from here, we want to know what is H equals to. What are you going to say there? If I'm to ask you, let's solve it, this one. Which means we are having 2H squared. You write your 2H squared is equals to A squared. Can you see A squared on the right? Then you move plus A squared over 2 to the left. It becomes minus A squared over what?
Over 2.
Over 2. Can you see? That is. Then on the left hand side, which means you are going to have 2H squared is equals to what? What is A squared minus A squared over 2? If it's A squared, which is full, you can write it as 2A squared over 2 if you want them to be the same denominator. Because A squared is the same as 2A squared divided by 2. Because the 2 and the 2 cancel, and then you're just having A squared. You are just manipulating so that the denominators are the same, then it's easy to subtract the what? The numerators. So 2A squared minus A squared, what do you get?
1 over 2.
A squared.
You get A squared. Over what? 2A squared minus A squared.
Isn't it A squared minus A squared over 2?
Yes. What is the answer?
Isn't it half? I thought we were going to get 1 over 2.
No, it's not half. It's A squared over 2. The answer is A squared over 2. It's not half. The answer is A squared over what? Over 2. Can you see?
Okay.
But it's not like it's the same as 1 over 2 times A squared. It's the same. It's the same.
No. A squared over 2 is not the same as half. That's what I'm refusing.
I say
A squared
over 2 is the same as 1 over 2 times A squared.
Yes, 1 over 2 times A squared. But did she say 1 over 2 times A squared, or she said half?
I just said half.
Yes, that's what I'm saying. That is not correct. But if you had said half times A squared, I would accept that.
Oh, A squared minus half a squared. It's yeah.
You get it?
Mm.
Yes. So let's agree. So that if you are not correct mathematically, let's agree. Yes. So that's why I used to manipulate using to say I can use the denominators, same denominators, to say if it's giving me problem, let me use, our original question was like this, isn't it?
Mm.
So which means I said, since that A, what should I do to make it having the same denominator? I manipulated. Then I said, let me add it as a fraction. Since it's a whole number, let me make it a fraction of a denominator 2. Because fractions, they say, if my denominators are the same, then I can be in a position to subtract what? Numerators. So I manipulated by putting a 2 on the denominator, and then I added a 2 on the what?
On the numerator.
Without changing the value of a squared. It's still a squared. So I just manipulate in such a way that my answer now is going to be equals to a squared. 2a squared minus a squared, I get a squared. Then the denominator does not change, it stays the same. So our situation now, it's saying 2h squared. So we are having a situation here where we are saying 2h squared is equals to a squared over 2, like this. Are you there? 2h squared is equals to a squared over 2.
Over 2,
So
yeah.
which means if I want h squared, what am I going to do?
You multiply
If I
both
want,
sides by 2. You divide both sides by 2.
I'm going to divide by 2, which means my h squared is going to be equals to a
8
squared over
over 4. A squared over 4.
4 over 4. Can you see?
Mm.
So if my h squared is a squared over 4, I want the value of h over a, to say what is h over a. That is the ratio which I've been asked in my question here. If you go to the question, it's asking for the ratio h over what?
A.
Over a. For this, for what value of the ratio h over a is every axis through the vertex a principal axis? It can be only a principal axis if all the moment of inertia in the x, y, and z, they are equal. That's why we equated all the moment of inertia that we got. We equated the equations. Now we have arrived at a point that h squared is equals to a squared over h. But my question is saying, what is a over h? You come and write that h squared, then you divide both sides by a squared, which means you're left with a squared. You divide both sides, you'll be left with 1 over 4 when you divide both sides. Can you see? But the question is saying, what is h over a as a ratio? Which means I'm going to put the what? Square root.
Square root, yeah.
On both sides. So if I square root the left, I must also square the what? The right side, like that. Can you see? What is the square root of h squared? It's h. What is the square root of a squared? It's a. What is the square root of 1? It's 1. What is the square root of 2 or 4? It's 2. So
We are
that
going to
value
have h over a equals to
is
1 over 4 square root. Square root of 1 over 4.
no, square root of 1 over 4 is half. Isn't it? You take the individual square root of 1, isn't it?
So it's going to be h over a over half. It's equals to half.
Yes, that is the ratio which you are looking for. That is the ratio that you are looking for. To say h over a is equals to half. We've arrived at the point. H over a is equals to half. Can you see?
Mm.
All right. So now when we are calculating the center of mass from the vertex along the axis. So now we are calculating the center of mass from the vertex along the axis. So which means the center of mass from the vertex along the axis. So for a uniform solid, for a uniform solid, which means along the Z, center of mass of the cone. Remember, we are talking of that cone. If it's a uniform solid for a cone only, the center of mass is positioned at 3/4 of the what? Of the height. For a cone, the center of mass along the Z is positioned at 3/4 of the height. All right. So now you want now to calculate, which means the moment of inertia along the center of what? Do you get it now? We are saying the Z center of mass of this cone is located. We only mean, isn't it, this cone is in 3 dimensions?
Yeah.
So when it's having coordinates. The coordinate for the Z center of mass is positioned, if we are looking for the center of mass, that point where we can find the center of mass of the cone along the Z, it will be 3/4 of the height when you are using the height of the cone. That is where it's positioned, the center of the mass of a cone. So the principal moments about the center of mass, the axial moment about the symmetry axis is the same whether taken about the vertex or center of mass, which means it's the same line. That is the axial. So what they mean is that whether you are going to take this side and that side, the center of mass will still be located at 3/4 of what? Of the height along the Z. That is the central part, where the weight, the center of mass. So if you want to calculate the moment of inertia along Z, center of mass, remember, what did we calculate at first for moment of inertia along the Z? Yes. So we come here. The moment of inertia along the Z was what? 3/10 ma squared, isn't it? Yes. So this is our 3/10 ma squared along the Z center of mass. Along the Z center of mass. Then along the X center of mass. So we are saying along the X center of mass is the same as the moment of inertia along the vertex. This is the moment of inertia along the vertex minus, which is the mass, and then g squared. All right. So we are going to take the moment of inertia along the X that we calculated, then subtract the mass, and this d, which is being squared, the d that is being squared, which is the height minus the height, that distance, which is being squared, 3/4 of h, and then you square it, which means the distance from the center of mass. Remember, this is a vertex, and the center of mass is somewhere at 3/4 h. Let me draw it nicely. This is our vertex of the cone, like this. This is the Z. This is the Z. Passing through the center. So which means this is the vertex. So if you want the moment of inertia along the X center of mass, which means you know that the center of mass is here. The distance, it's the center of mass of the cone, it's at 3/4 h. That is the center where the moment of inertia it is. So I'm going to subtract that distance squared, which means mass times that distance squared from the original moment of inertia. Mass times distance. So which means this is the original moment of inertia, which we calculated for the moment of inertia in the x, minus the moment of inertia, which means this we multiply the mass multiplied by the center of mass of this cone. We say the center of mass of the cone, this D, which means that is the position of the center of mass. Since now we are not only calculating the moment of inertia along the Z, but we are now calculating the moment of inertia along the X at the center of mass. So we have subtracted, which means it's mass times that center of mass, the distance to the center of mass, which means it's 3/4 h. Then you square it. So this is just a formula that you must just know. This one, which means if you want to find along the center of mass. But if you just want the moment of inertia in the x, you use the 1y² plus z². But if you want the moment of inertia along the center of mass, which means it will be ix minus the mass multiplied by the d, which means up the distance to the center of mass. So now you just use the arithmetic to sort everything out. If you want, we can assist you here. Let's multiply together. How do you manipulate the right-hand side if you have to subtract? So this will be 3m
h² over 5.
over 5. Then it's subtracting. This one, it is h², isn't it?
Yeah.
And then there's another one plus what? 3m
h² over 20.
Hello?
I think it's network problem.
Yeah. Let's join again.
Okay.
Typo. I'm supposed to leave. What? Coming of this?
I think maybe his computer is off because it was saying it is 5%.
Oh, the battery. Yeah, the battery is low.
Yeah.
I
I think it's a
guess
bit.
we'll continue.
Now I'm tired. You are Bye.
Now.
Bye. Yo, Kimi.
Yeah, I'm tired also. I'm gonna continue. But if we're continuing tomorrow, it was gonna be fine. No, I
Yo,
don't mind.
okay. Why?
Yeah.
Utswil.
Sweet.
Oh, Logan.
Hmm?
Tomorrow is Friday. I'll
Friday.
know. So,
I don't.
letla go kae ka practical mar.
Eh?
Di boima. Ke ra practical. Di boima
No.
mar.
No. You're not hard.
Di a ngwaleha ne.
Yeah.
Re tswenyana ka dictation wena ya mahalanyana so. Motho wena o tla ka ya physics nyana ya mathomo a ka phasa shapa kere. Remember I told you. Re no tshwaranyana 80 nyana 90 wena. Ka nnete. A re ife mme o la. O kry-ile bokae ka assignment 1 yo wa timana mme o la ka dimaraka.
Yeah, as I went at least. I got 50 something. I failed. No, not that I failed. I just got. I think I
Maybe
got 58.
I got 51. Nahan.
Too
What dimana shem? Kadi maraka.
much. Oh, wow. Like, I'm like, what is it? Is that right? Or Panama? Huh?
So what are
She
you
said
going
the
to do?
she said the memory.
Huh?
Like looks like I wrote just that, like I did not write the same as the memo, but then most of the things, yeah, I just don't understand why I got so low.
Or rumekile memo?
Didn't It's not there.
I don't know.
I think I
I
saw the
didn't
memo.
go through the paper. I just saw it on my admin there.
Hmm. I don't know. Maybe I'm mixing modules, but
I'm also not sure. I didn't check. Maybe we have. I just saw it call my admin. I wanna call the results. The all the
mm,
assignments. Eh.
mm.
So what are you going to do, Katela? That you're supposed to draw using the PC? Ushota katsona no.
Yeah, but then I'll just print it out. The group, my group mates.
Hey, I didn't Nashem. I'm not coming with a computer. Go Joburg. Nah. Hi, I have one when kung kang exam. Like
That's
yataba.
fine. Okay.
Rita irana mo groupung. Ay, ngeke shem. I also have
Yeah,
another
actually,
guy.
I need to finish today the work tomorrow so that tomorrow I submit it. It's
Hey,
straight.
also tomorrow is Friday, and you have to go back home.
I'm not going back this week.
You have another practical.
No, I don't have another one. Mm.
Hmm?
I don't have another one, but I'm not going back. Just.
So hey, Atum. And then when Haibo. Ah,
No, I'm not gonna go
then
now.
ukre muthu mo Joburg. You have to. Wow, so do you know how people are excited to go home on Friday, Mara? Like ripakile. And then when Haibo. Yo, okay. Yeah, ne? Let me not judge you, Shem. Your life. Haibo. Eh. Like I'm always excited to go home. Not all the time. Guru one mark. Hey, yeah, ne?
Hey, let me just write you. Bye bye.
Bye.